Alright everybody, welcome back to another video. In this lesson we're going to be discussing how to actually add some gameplay to our MMO. Because currently all that we can do is log in and chat, but by the end of this video you'll be able to log in, load into a game, and then log into the game on another client as well, and you should be able to interact with other players. So you can see on the right hand side here, I can zoom out and see the player that I'm controlling in the left window. So if I just swap these windows around, we can make these players come to each other, and we should see this player pop through on the right screen now as well. And as you can see, the movement is not perfect, but if you stick around till the end of this video and then to the beginning of the next video, I'll show you how to smooth things out and make the gameplay feel a bit nicer. And as always, if you're following along at home, you can always come to my blog, tbat.me, come to the project section, and then just click on this Godot for Golang tutorial series. And we're up to lesson 6, so scroll down to this section here, and you can follow along the text version of this post on this page. If you want to check out the code up until this point, you can come down to here where there's a link to the release on the official GitHub repository, and you can just download the source code here and then import that into your project. But for those of you who have been following along so far, let's get started. So we're going to be adding a new state to our server, and this is going to be a new state which gets transitioned to from the connected state after the player has logged in. And it's going to be responsible for handling player actions related to gameplay. So every time a player changes direction, or every time we receive a update from another client relating to a player or player's information and stuff of that nature, we want this all to be part of this new state. We're going to call this new state the in-game state. But before we need to worry about any of that, we need to actually allow the server to represent a player. We need to be able to store players and all of the information that pertains to them so that we can pass it around and send it to the client and things like that. You might recall from part 3 that we have a way of storing things on the server in a thread-safe manner and pass them around between different processes. And that would be our shared collection custom data structure. Let's go ahead and add another file to the objects package, and this will be for game objects. These are going to be objects that we can store inside our shared collections, and then they can be easily passed around. So right click on the objects folder and select a new file, and we'll call it gameobjects.go. It's going to belong to the objects package. And the first object we're going to create for now is going to be the player object. Type player struct. It's going to contain a name, which will be a string, an X, which will be a float 64. This is a double precision floating point number, and so will Y, and so will the rest of the properties that I'm going to define here. We'll have radius, direction, and speed. These are all the things that make up a player in our world. Next is going to be, how do we store objects in the hub? We already have a way of storing clients in the hub, just by a client ID and a reference to their client interfacer. But in order to store objects, there could be many different kinds of objects, like players, spores, you name it. So we're going to create a wrapper that can hold different kinds of game objects in collections. So we're going to call it shared game objects, and we're going to define it in hub.go. So shared game objects struct is going to have a member called players, which is going to be pointer to a shared collection, which is going to hold pointers to player objects. And it will be most convenient for us if we insist the ID of each player is going to be the same as the ID of the client that owns it. So I'm just going to leave this comment here that says the ID of the player is the ID of the client, and that way we can be reminded every time we hover over the players member of our server's shared game objects struct that this is indeed the case. And we'll make sure that this is the case later on when we add players to this collection. And in the future, there'll be many more members here. So we'll have spores and whatever else we like. But for now, it's just going to hold players, and we're doing it this way just for future-proofing reasons. Let's add a reference to this struct in the hub. So let's scroll down to where we're defining the hub struct, just here. And let's add shared game objects, which will just be a pointer to the shared game objects struct that we defined before. We can initialize this shared game objects member in the hub's constructor. So under new hub, let's make shared game objects equal to a new shared game objects where the player's member is just going to be a new shared collection of pointers to player objects, and we're using the new shared collection constructor that we defined in our custom data type in part 3. We need the client interfacer to be able to access the shared game object struct, so let's add the following new method to the client interfacer interface. So here's our client interfacer interface. These are all the methods that it requires. And just here before the close method, let's add shared game objects. It's a method that returns a pointer to a server's shared game object struct. When we save this file, now the Go compiler is immediately complaining to us that our websockets.go no longer implements the client interfacer. So let's go ahead and fix that up. So open up the internal server client's websocket.go file, and we just need to implement this shared game objects method. So let's do that here. Shared game objects returns a server.sharedGameObjects pointer, and we're simply going to return c.hub.sharedGameObjects. And now the compiler is happy with us again. So now we have the ability to create a new player object, and we also have the ability to store it inside a shared game objects struct, inside a player's collection that is going to be shared between the hub and each and every client interfacer. So let's create our new state. So under states, create a new file called InGame.go. It's going to belong to the states package. And let's define the underlying struct that's going to hold all the information for this state. So type InGame struct. The first thing it needs is obviously a reference to the client interfacer. And if I press Ctrl S, it should automatically import that for us. We're going to need a reference to a player, which is the player that we control in this state. So player is a pointer to an objects.player object. And finally, we'll just need a logger, log.logger. Now, in order to implement the state handler interface, we're going to need to implement each and every method. I think there's 5 methods that we need to implement, and these are laid out in hub.go. So if we search for the client state handler interface, these are the 5 methods we need to implement on our in-game state. So let's drag this to the right so we can keep track. And let's start with the name method. So I'm just going to simply refer to my in-game state as a lowercase g for game. And let's simply return in-game for the name method. For the set client method, we can copy and paste what we've done for the connected state. It's just going to be initializing the logger and injecting the client into the state. So I'll just copy the body of this set client method on the connected.go state, and I'll paste it here into the ingame.go. I'm just going to replace every instance of c dot with g dot. And we don't need to keep a shortcut for the database queries and the database context because we're not going to be accessing the database as much in this state. So it doesn't really warrant having a whole new member dedicated just for that. I'll just press Ctrl S to import the format package. Next, let's implement the onEnter method. Here's where we're actually going to be adding ourselves to the server's shared game objects collection. So we'll go log.printf, adding player placeholder to the shared collection. g.player.name is what we'll put in there. And then Copilot's figured it out. We're simply going to call the shared game objects method on our client interfacer and then access the player's member. And because this is a shared collection, we can call our add method and then supply the player object. But remember, the ID of the player must be the ID of the client. So conveniently, we've allowed ourselves to supply an optional parameter to the add method of our shared collection data type. And this is an optional ID. So it adds an object to the map with the given ID if provided. You can leave it blank and it will auto assign you one. But in this case, we know we want the ID to be that of the client. So let's supply g.client.id. Next, let's implement the handle message method. We're just going to leave it blank for now, but we need to put something there just to satisfy the compiler. And if I press Ctrl S, it should import the packets package for us. And finally, we'll just implement the onExit method, where we're going to clean up by removing our player from the shared collection. So g.client.sharedGameObjects.players.remove g.client.id. It's just one more thing. You may remember from part 3 that the shared collection methods, there's a chance that they might get blocked, and there's a chance that you might need to wait some time for other processes to finish using them. So that they may be a lock on the shared collection while something else is adding to it or while something else is iterating over it, and we need to wait before we can actually add to the collection. Because we don't know how long we're going to need to wait, and our state is ready to go and start processing packets as soon as possible, we're going to run this add method in a Go routine, just by typing the word Go in front of that line there. We can do this when we don't really care about the result of an operation, we just care that it gets done at some point, such as this. So let's save our ingame.go state, and now we can look at transitioning into this state from the connected state when the client successfully logs in. So if we come to the connected.go state, find the login request handler, which is here, there's going to be a section where we can see that we've logged in successfully and sent a OK response back to the client. It's here that we can go ahead and transition into the in-game state. So we can say c.client.setState, and then we're going to create a new in-game with, well, the only thing we know about the in-game state at the moment is we can supply a new player. So let's give it a player of objects.player. And the only thing we know about the player is its name. The name of the player is going to be equal to the username that we got from the login request message. So player name is username. So just as a quick sanity check, we should actually be able to run the server again and connect to it. And if we follow along with the server logs, we should see that the connected state transitions to the in-game state, and then the in-game state will log a message saying that it's added a player with the given player name to the shared collection. So let's look at our debug console and open up Godot. Click run. And as soon as I log in, I'll just have to register real quick and then log in. We should see switching state from connected to in-game and then adding player to the shared collection. So that looks good to me. I'm just realizing we're not actually logging using our custom logger, so we should probably do that. Instead of log.printf, we'll do g.logger.printf. Just a small thing, but there's no point having a custom logger if we don't use it, right? Okay, so now that we have a brand new state ready to start handling messages, let's go ahead and create some new packets. So we need 2 new packets. One is going to be sent from the server to the client to give it all of the information it needs to know about its player or about other players. Another packet will be sent from the client to the server to indicate that it's moved. So when we move our mouse around the screen, it's going to send a message to the server to say, hey, we're now moving in this direction. It's going to be the server's responsibility to then calculate what that means and then send update packets to all the other connected clients. But we'll get to that when we get there. For now, we're just going to define the packets. So come to our shared/packets.proto file. We'll add a new message called a player message, and it's going to have a fair few things. It's going to have pretty much everything that makes up a player. So first and foremost is the ID of the player, which is going to be an unsigned 64-bit integer. And then we'll have the name, which will be a string. And the rest are all going to be doubles. So we'll have X, Y, we're going to have a radius and a direction. And finally, we'll have a speed. So these are all the things that are going to make up a player. And we can send this kind of thing to the client. Let's also make a player direction message. which is just going to contain one thing, which is the direction as a double. So this will be the angle between 0 and 2 pi radians, or 0 and 360 degrees. And this is only ever going to be sent from Godot to the server. So we don't need to include an ID associated with this message because we already know this message is only ever going to come from our client. Now let's just register these message types into the possible messages that will be bundled with the packet. And as I press Ctrl S, it's going to recompile into my Go code. But if you don't have the VS Code Proto 3 extension installed, you can go ahead and run this command from your project directory. But regardless, we need to run the Godot buff plugin. So come to Godot, and next to the file system tab, we have the Godot buff tab. And we'll just go up a level for the input and select packets.proto in the shared folder. And for the output, we are going to select packets.gd. Just click compile, and there should be no errors. So we're done with our packets.proto file, we can close that. Now, every time we add a new packet that can be sent from the server, it's a good idea to go ahead and add to our list of helpers in our pkg/packets/util.go file. So here are all of our helper methods that allow the server to easily construct these packets, because otherwise it's too long-winded to do so on the fly. So let's create a new function called new player. And the benefit of doing this is we can actually supply not only an ID, but also an entire player object if we just import the objects package. This will allow us to really easily create new player packets. It's going to return a message, of course, just like the rest of them. We're going to return a new packet player struct with the player member being a new player message. And all of these fields are going to come, well, except for the ID, but all of the rest of these fields are all going to come from the player object. It's just going to be like for like. So x, player.x, y, player.y, radius, direction, and speed. So when do we want to actually send a new player message to our client? Well, as soon as the in-game state is reached, that would be a good time because the user's just logged in, and the very next piece of information they're going to want to know is what is my player, how big is my player, where is my player, and all of that. So we can close our util.go, and inside our ingame.go state, we have our onEnter method, which we're already using to add our player to the server's shared game objects players collection. But just underneath that, let's set the initial properties of the player and then send the player's initial state to the client. So we'll just go through one by one. So g.player.x, we're just going to choose a random x coordinate. So we'll go rand.float64. So this will give us a random number between 0 and 1. And we'll just scale that up by 1000. When we press Ctrl S, it should import the math/rand/v2 package for us. And we can go ahead and do the same for y. For the speed, we're just going to hard code that to 150. And same with the radius, we'll just hard code it as 20. Now we can use our helper function. So g.client.send.socketSend packets.newPlayer, and we'll give it the ID, which we know is going to be our ID. And it's also going to be equal to the player's ID, which we know is going to be equal to our client ID. And we'll give it the g.player object. So this is going to send a new player message with all of the information that our player object holds straight to Godot. And by the way, we're setting all of these attributes on the player object after we add it to the shared collection. That's totally fine. Our reference to our player is being stored inside the player's collection, and that's never going to go out of date, even if we modify it after the fact. The reason for that is that the player's collection is only holding pointers to player objects. So these are just memory addresses. So every time it wants to grab some information about our player, it has to look up the memory address, and it's going to find the same place in memory that we are holding onto. And when we update member variables on our player, everything is just going to be in sync. So we don't need to worry about updating the player's shared collection or anything like that. Okay, so we're now sending the player's initial state directly to the client. So we need to now go ahead and start rendering the player once it's received from the client side. So let's open up Godot. We're going to create a new folder under res, which is just going to store all of our objects. So let's call this new folder objects. And for now, we're just going to have one subfolder called actor. So an actor is what I'm going to refer to as a general player. So I might make a distinction between players and actors. Basically, a player, I'm going to say, is the actor that we control. So us as the player is going to control the player actor. Otherwise, a general actor could be our player, but it could also be a different player. It could be a networked actor. So just to keep things general, I'm going to call this folder actor. And then inside the actors folder, I'm going to create a new scene called actor.tscn. And it's going to inherit from an area 2D. So an area 2D is just a shape which has a hitbox. And that's all we need, just a way to detect collisions and some sort of shape associated with that. So let's create our actor.tscn scene and open it up in the 2D scene editor. So the very first thing that Godot is complaining about is that this node has no shape. So if we select the area 2D, the whole point of the area 2D is that it can have collisions. So we need to go ahead and give it a collision shape 2D. So let's add a new child node and search collision shape 2D. And we're getting another warning that we must give it a shape. So with the collision shape 2D node selected, come to the inspector and under the shape property, click this drop down and we'll give it a new circle shape 2D. So that satisfies the warnings. And we also get a little circle centered at the origin. So this is our hitbox for our actor. An actor is also going to need a nameplate. So let's add a new child node under the actor root node, and it's going to be a label. And just to make things a little bit easier, let me rename this label to nameplate. And I'll just put some test text in here because we want to center this label on the circle. So I'm going to select center for the horizontal and vertical alignment. And then for this preset anchor, I'm going to choose the center preset, and that centers the text on the circle just like that. So I can get rid of this test text here. And lastly, let's add a camera 2D node, and we'll leave these settings default, but if you scroll out, you can see this faint purple rectangle. This is the camera's viewport. So we can use the camera to follow the player, and we can zoom in and out as the player grows. So very importantly, we need to make sure that the hitbox for this actor is unique to it. So what does that mean? Well, if you come to collision shape 2D, if you select the circle shape 2D shape property in the inspector, it gives us some more options. Some more options are under this resource section. So expand the resource section and make sure you check this checkbox next to where it says local to scene. So what this does is it ensures that the collision shape 2D's hitbox is unique to it, and it's not going to be shared by any other actors. So there might be multiple actors all around the game, but they each will have their individual hitboxes. So this is very important. Just make sure local to scene is checked and we can save our scene. Let's attach a new script to our actor called actor/actor.gd. And in this script, we're going to provide a very easy way to instantiate new actors and add them to a scene. So in our in-game scene, it should be very easy to, on the fly, create new versions of these actors and then place them all around the map. Because of that, we're going to need a constructor, and we're going to treat this thing kind of like a class. The other thing this script is going to be responsible for is taking the input of the player. So if the player owns this actor, the player should be able to move their mouse around, affect the position and the velocity of the actor, and then send player direction packets to the server. So without adding everything all at once, let's just start by adding a list of things that is going to need to define an actor. So it's going to need an ID, which will be an integer. It will need a name, which will be a string. It'll need so an area 2D will already have a position, but we need to keep track of the start position. So let's go start X, which will be a float, and start Y. Same thing with the radius. We're going to keep track of the radius, which can change, but we also need to keep track of the start radius. And the speed doesn't change, so we'll just call that speed. And we'll also need a notion of whether or not this is the player actor or if this is a networked actor. So we'll just say is player is going to be a bool. And you might notice that we're missing direction. So direction is going to be encapsulated by velocity. So let's create a member called velocity, which is going to be a vector 2. So now we can create an instantiate function, which is going to serve as kind of the constructor for this class. So it's going to be a static function. It's going to be called instantiate, and it's going to take in all of the parameters that we see here. I'll just call this X and Y, and radius, and isPlayer is also going to be passed in. But what does this thing return? Well, it's going to return an instance of itself. So this script is basically going to need a way to refer to itself. So for that, we're going to type const actor with a capital A, which is what we'll call ourselves. And that's going to be equal to preload. And we're just going to type the path to this script. So objects/actor/actor.gd. And we can say that this instantiate function returns an instance of an actor. So how are we actually going to create an actor and then set all of the properties and then return it? Well, this actor scene is what's known in Godot as a packed scene. So this itself can be treated like a resource that can be loaded. And the scene, every packed scene will have an instantiate function as well. So let's call this by scene with a capital S. And we're going to preload the scene. Res objects actor. And instead of actor.gd, we'll go actor.tscn. And it's this way that we can say var actor equals scene dot instantiate. And you can see that this returns a node. In our case, it's going to return the actor node. So we can say actor dot actor ID, and we should be getting IntelliSense hints here, but we don't. And the reason for that is Godot has not recognized our list of properties yet because we haven't had a chance to save this script while there are no errors. So let me just comment out this problematic piece of code. It was just an error because I hadn't finished typing the function. So now this script is free of errors. I can press Control S. And now if I uncomment this code and continue trying to type what I was trying to type, I can type actor dot, and now it gives me some IntelliSense. So actor ID equals actor ID. Actor dot actor name equals actor name. Actor dot start X equals X. Start Y equals Y. Start radius. And we've got speed. And lastly, actor.isPlayer equals isPlayer. After all that, we can simply return our actor. So this is going to be a way to obtain an actor node from our other scripts with all of these properties. And what you can do with that node is add it to a scene. So we're going to have a in-game scene, and from this scene in our script, we're going to be listening for player packets from the server. And every time it receives a new player packet that we haven't encountered, it's going to use our instantiate script to make a new node and then pop that straight into the scene tree. Let's come back to our actor.gd script because we still have to incorporate the logic for when the node is ready and when the node is running around and taking input from the player. We also need to draw the actor as well. So let's start with the node's ready function. So this is a built-in function called _ready, and this is called whenever the node is added to the scene. So we can set the position property on the area 2D, we can set the positions x equal to start x, and the positions y is going to be start y. We can set our velocity property, and we should just set it to some random direction, or whatever direction you feel like, multiplied by the speed. So if someone joins the game and their window is out of focus or something like that, we don't want them to just sit there with no direction. We're just going to give them some sort of direction of vector2.right. So that'll be a direction pointing right, and the speed that we have is going to be the velocity's speed as well. And we'll set the radius equal to the start radius. We should also set our collision shape and our nameplate. So let's grab references to that. Let's just do it down here. I'll drag over the nameplate, hold control, and then release the mouse button. And I'll just put a leading underscore just to indicate that this is not to be accessed from outside our script. And let's give the same treatment to the camera, except I'm just going to call this camera. We already know it's a camera 2D, so no need to call it a camera 2D. And I'm just going to manually type the collision shape because it's going to be a little bit different. So I'm going to call it collision shape, and it's going to be a circle shape 2D. So we're going to be a little bit more specific about it because this thing's a collision shape 2D, but we're going to have it as a circle shape 2D, and it's going to be equal to the collision shape 2D's dot shape property. So let's come back down to the ready function, give ourselves a bit more room, and let's add the collision shapes radius equal to our radius, and let's set the nameplate's text just to our name. Now we're also going to override the physics process function. This is another inbuilt function that gets fired every physics frame. First thing we're going to do is update our position according to our velocity. So position plus equals velocity, and we're going to want to multiply the velocity by this delta. So we're essentially scaling the velocity vector by either a small amount or a big amount, depending how laggy our game is. So if our game is running really smooth, delta is just the time that has passed since the previous physics frame. So if our game is running really smoothly, delta is going to be really small, which means we're going to want to scale down the velocity step each time we update our position. We'll only want to increment the position by small amounts, so we scale velocity by a small amount. If our game is really laggy, the time between physics frames is going to be quite large, so delta is big, therefore our position step is going to be big in order to maintain a consistent speed. So this is not a concept that's unique to Godot. You've probably heard of this concept, and you should definitely familiarize yourself with the concept because we're going to be sort of creating our own delta time once we start trying to sync the player's position on the server. So this is all we really want to do if we're considering a networked actor. But if it's our own player, we're going to want to grab input and send direction packets to the server. So in order to separate these two concerns of logic, we're just going to put a early return here if we're not dealing with a player. So if not is player, return. And then we know that everything below here is player specific logic. First of which is going to be obtaining an input vector. So let's say mouse pos is get global mouse position. And then we can use that to calculate an input vector, which is just going to be the angle between the player's position and the mouse's position. But we just want it to have a length of 1, so we're going to need to normalize it. So we'll type position dot direction to mouse pos dot normalized. So that's going to be a vector pointing in the direction that we're trying to move, basically. And because we don't want to spam the server with a million different direction messages every time we move our mouse just a tiny bit, we want to reduce the granularity of our game ever so slightly. So instead of having full control of all 360 degrees of a circle that you can move your mouse in, we're only going to consider breaking the circle up into like 15 parts. So each segment, if you're within that segment, we're not going to be changing direction, we're not going to be sending a new packet. But if we cross to another segment, then we can go ahead and change our velocity and send a new packet. So the way to do that is if the absolute value of the angle between our current velocity and our input vector, so velocity dot angle to input vector, is greater than 2 pi over 15. So this is us breaking the circle into 15 evenly spaced segments. Then we can say velocity equals input vector times speed. And I just typed is instead of if. And just because I'm a maths nerd and because the Godot engine has this keyword, instead of typing 2 pi radians, I'm just going to type tau, which is just the same thing, but I think it's pretty neat that Godot has a tau keyword. And by the way, 2 pi over 15 radians is about 12 degrees, or it is exactly 12 degrees. So we've updated our velocity. Now let's construct a new player direction message and send it off to the server. We'll just do that in the usual way by creating an empty packet. And before we can do that, we need to actually import our packets. So let's just do that at the top here. Const packets equals preload res packets.gd. Come back down to the physics process and we need to create a player direction message using the new packet, packet.new player direction, and then we'll set the direction on this new message, player direction message dot set direction, and we'll just give it the velocity dot angle. We could have also given it the input vector's angle as well. Doesn't matter. They're both the same. And then let's just send that off using our WebSockets singleton. So ws.send packet. So that's it for our physics process function. The only thing left is to actually draw our actor, because at the moment we can see that there's a blue circle, but this is only showing the hitbox to us because we're in the editor. Once we load our game, this blue circle will not be drawn. So we're going to need to override the draw function. And this gets run once when we create the node, but this won't be run every frame. If we want to actually redraw an object, we need to call a special function called queryDraw. So we'll get to that later once we start increasing the actor's radius. But for now, we'll just draw a simple circle. The position we need to remember is relative to the area 2D's position. So because we want to draw it right on top of the area 2D at all times, we'll just use vector2.0 as the position argument. The radius argument can either be radius or collision shape.radius. They're both the same, so it doesn't really matter. And for the color, we can just choose a nice purple color, so dark orchid. Okay, so that's it for now for our actor.gd script. It's kind of a long one, but it has a few different responsibilities. So now that we have a way to easily add a new actor to the game, let's get the in-game state listening to new player messages, and then we can actually start adding these things to the world. So I'll close our actor tab, and we're just going to focus on the in-game scene and the in-game script for now. So we're going to need a reference to our actor script. So let's go const actor with a capital A equals preload res objects actor.gd. And let's start listening for player packets in our onWebSocket packet received handler. So let's add a new case here. So elif packet.hasPlayer, and we'll just redirect to a new handler function called handle player message. And as usual, we'll give it the sender ID and the packet.getPlayer. So let's define this handler just underneath where we've just defined the chat handler. Why not? Sender ID. So what we need to do for now when we receive a new player message is we're going to unpack all of the information that was bundled inside that message. So things like the ID, the name, the position. We then need to calculate whether or not this was our own player or if it came from a different actor. And then we can use our instantiate function from actor.gd to get a new node, and then we'll add that node to the world, to the scene. So unpacking variables, So you'll notice we're not actually unpacking the direction. That's just because the direction is calculated as soon as it's added to the scene via the onReady method. And we can actually use the direction later on. But for now, we just want to get this thing shown on the screen. And we don't really care about if it looks janky or not at this point. That can be for the next part. Let's calculate whether or not this was our player. So isPlayer is going to be just whether or not the actor's ID matches our game manager.client ID. So this is the benefit of having each player's ID equaling the client's ID. We can easily tell if this came from our player or not. And finally, we can instantiate the actor. So actor equals actor dot, we can use our static function instantiate, and we can already see it's asking us everything that we need to fill out because we statically typed all of these things. So actor ID, actor name, XY, radius, speed, and isPlayer. Finally, we can now add it to our scene, but there's not actually a good place to add just yet. In our scene tree, all we have is a node and a canvas layer. Let's add a new node to our in-game node, and this will just be a node 2D, which is a special spatial node where you can add things that have positions and sizes and things like that. So this is where we're going to be adding all of our game objects. So because of that, we're going to call this world, and I'm just going to make it appear first, but it doesn't really matter. We'll come back to our in-game script, and now we can say we need to get a reference to our world. So I'm just going to click and drag, hold Control, and release the mouse button. I'll add a little underscore there just to make sure it's private. And now we can finally say world.add child actor. So now this is everything we need in order to get an actor spawning based on a player message. So we'll see how that works if we run our server and then run the game. We can log in and we see our player with our player's name, the radius, and supposedly we have some sort of speed and direction, and we can change direction and send packets. But we currently have no evidence of that because the background is just a static gray color. It's impossible to tell if we're moving or not. So let's fix that first. We're going to give our world node a texture, just a simple tiling texture to make it apparent when we're moving. So if you come to my blog, tbat.me, under projects, Godot Golang MMO tutorial series, and lesson number 6, if you scroll down a bit more than halfway down this post, you'll see this texture here. So you can right click, save image as, just keep the default name of floor.svg and save it to your downloads folder. Now, if you open up your file explorer, navigate to your downloads folder, you can click and drag this to import it. But first, let's create a folder to drag it into. So under res, create new folder. We'll just call this resources. And this is where we're going to store basically all of our assets for the game. So now we can drag floor.svg into the resources folder. That will automatically import this as a texture. Looks like I failed to drag it into the resources folder, so I'll just do that now. So it should be floor.svg under resources. This is a texture resource, something that we can use in a sprite. So under the world node, add a child node. We'll add a sprite 2D. And then we can just click and drag our floor.svg into this texture property here in the inspector. We want to tile this to cover the entire map. So under region, we're going to enable regions. Set the width and height to say 10,000 each. And then under texture, we're going to select repeat enabled. And that will go ahead and tile our region for our texture. And I'm just going to rename this to floor, but it doesn't really matter. So if I save that and run the game again, log in, and we can see that we're moving around. And if I move my mouse just a little bit, it's not going to change the direction or send any packets. But if I change it more than a 15th of a circle, we start to change directions. And this will just help us cut down on spam on the server. It's not as important for us to have crazy high fidelity in this kind of game. So now that we're sending direction messages to the server, we're going to need to keep an accurate representation of the player's position on the server. This is going to be used for sending updates of each player to all the other connected clients, so that each client can then in turn keep an accurate representation of each other player. So in the in-game state, let's create a new function called sync player, and we'll give it a delta argument, which is going to be a float 64. So delta is going to represent the amount of time that has passed since we last called this function. And we're going to use that to calculate, based off the player's direction, the next X and Y coordinates, move to those coordinates, and then broadcast this change to all of the other connected clients. So you might be thinking, how are we going to get the X and Y coordinates based just on the direction? Well, for those of you who remember basic trigonometry, you're in luck, because we're going to need to use that. So I have here a diagram, which allows me to control a direction, which is just a number between 0 and 2 pi. And I can also control a speed. So this is how fast our player is moving, and then this is the direction in which they're moving. And you can see that based on just these two controls, I'm able to calculate this green dot here, which is exactly the player's X and Y coordinates relative to their previous X and Y coordinates. So if we imagine the origin is the current position, then this green dot is going to be the next position. So how is this green dot's X and Y coordinates being calculated? Well, just with these simple expressions here. So the X coordinate is just equal to the speed times the cosine of the direction, and the Y coordinate is the speed times the sine of the direction. So let's incorporate that logic. We'll say new X equals g.player.x plus g.player.speed times math.cosine g.player.direction. And we need to multiply this by delta. We want to update it by a lot if it's been a long time since we last synced, but we only want to update by a little bit if we've synced very recently. We'll just do the same for y, except instead of cosine, we're going to use sine. Let's update the player's position using this new X and new Y. And then we can form an update packet to inform every connected client about this change. And we can also use it to inform our own client about this change, because we don't want the client to be acting under any false illusions that they might be somewhere that they're actually not. So if the client is lagging out and they think that they're over in one area of the map, but the server thinks that they're still in the other area of the map, we want to basically rubber band the client's actor back to the server's last known position. So we're going to be sending updates to our own client as well. So let's form that update packet. It's going to be a player packet, and we'll use our new player helper function again. We'll give it the client's ID and the player object now that we've updated it. Let's go ahead and broadcast this out to all other client interfaces. And lastly, in a Go routine, just because we're dealing with sockets, we don't want anything to block, let's go ahead and send that straight to our own client. Now, because we are broadcasting this, that means that other states could be broadcasting it to our own client interfacer, which means we're going to need to come to expect it in the handle message method. So let's handle that now. If we receive a player message from a different client, we are just going to forward it onto Godot basically, but we need to write a handler for it. So we're going to switch on the message's type. And in the case where it's a player packet, we're just going to defer to a handler. So g.handle player, and we're going to pass in the sender ID and the message, as we always do. And let's create that handler. We'll do it just after the onExit method. So the first thing we can do is just a quick sanity check to see if we received it from our own client. That doesn't make any sense, so we'll just discard from that. I like these little sanity checks just to make sure I'm not ever shooting myself in the foot. But if we received it from a different client, we can go ahead and just send it straight to our client. And we'll use the socket send as method so that we can preserve the sender ID in the packet that we send to Godot. Okay, so now we are able to receive player update broadcasted messages and forward that onto our client. We just need a way to call this sync player method in a loop, in a regular loop in the background. So let's create a new function called update player loop. And it's going to take a context. And this is something that we can use to externally control when the loop should end. Because without this context, it's just going to be a little tricky to get in there and make sure that this thing stops gracefully. So you'll see how that works in a minute. But for now, we're just going to set a fixed delta of, say, 0.05 seconds. So 20 times a second is when this sync player method should be run. We can set up a ticker, which is a handy way to make something run in regular intervals. So time.newTicker, time.duration, delta, times 1000 milliseconds. So we just need to multiply it by 1000 because we need to have an integer, and we'll just use milliseconds as the time interval. So the first thing we want to do is ensure that the ticker actually stops when this method is returned. So that's why we'll defer the ticker.stop method. And then basically we're just going to run a loop, and in a select statement, in the case that the ticker ticks, we want to run the sync player method with the given delta. And in the other case, where our context is done, and we'll see how this works in a minute, we're just going to return, and that will exit the loop and make sure the ticker stops as well. So how are we going to tell when our context is done? What does that even mean? Well, in our in-game struct, let's add another member called a cancel player update loop. And it's going to be a cancel func. So this is something that we can call when we want a certain context to say that it's done, basically. So to get the loop started and to get this thing defined and pass in the context to the loop, let's go ahead and do that when the very first direction message is received. So in our handle message method, we're going to look for another case. So case when packets.packet player direction message is received, and we're going to defer that to a handler as well, which we'll define down here. All we're going to do is, if the sender ID is our own, so this direction message is coming from us, we are going to update our player's direction according to the messages player direction.direction. And then we just check if this is the first time receiving a player direction message from the client, then we'll just go ahead and start the player update loop. So if g.cancel player update loop is nil, so that's our cancel func. If it is nil, as in we haven't actually assigned it to anything yet, then we know that this is the first time that we've received a direction from the client, because the next thing we're going to do is go ahead and define and assign this thing a value. So we're going to say context and cancel is equal to context dot with cancel, and we'll just give it a background context. And then we can set the cancel player update loop to this cancel func. And then we can run in the background our update player loop with the given context. So then on the next time that we receive a player direction message from our client, this thing here is already going to have a value, so this whole block is going to get skipped. So in that way, we really only started on the first time that we receive a player direction. And now we have this handy member on our struct that we can actually use on our onExit method. So when the state's finished, we want to stop running the loop. So before we actually remove ourselves from the shared game objects, we're going to check if g.cancel player loop is not nil, then we can actually go ahead and invoke it and then do everything else. So this will tell the player update loop that its context is done, so it needs to return, and then we go ahead and continue cleaning up. So basically, if we run the game again at this point, what we're going to be doing is 20 times every second, we're going to be updating the player's direction therefore updating the player's position and then sending that update to our client. What that means for us, because we haven't actually told Go what to do when it receives a new player message from a player it already knows about, it's just going to keep adding the same player over and over and over again. And it'll eventually crash our computer if we let it run long enough. You can see that here. So our goal for the rest of this video is to keep track of players on the client and make sure that we're only ever adding a new player if we've never encountered them before. If we have encountered the player before and we receive a new player message, what we can do is go ahead and update their position, but we don't need to add them to the world again. So how are we going to track other players? Let's come to our InGame.gd script. And at the very top, we're going to create a new instance variable called _players. And it's going to be a dictionary. And this is a Godot 4.4 specific feature. We can have a typed dictionary. So previously, only arrays could be typed, but now we can actually type dictionaries and give it a type for its keys and a type for its values. So this is going to represent the ID, and this will represent the actor. We're going to keep track of all of that in this players dictionary. So where we're handling a player message, before we actually instantiate the actor and add it to the world, we first want to check, we only want to do this if we haven't encountered this player before. If actor ID not in players, then we can go ahead and do this because this is a new player. So we need to create a new actor. And lastly, in that case, we'll go ahead and assign this actor ID with our players dictionary. So players at key actor ID is going to have a value equal to this actor node. In the other case, when we have encountered this actor before, what we want to do is simply update their positions. We don't need to add them to the world again. So this is an existing player, so we need to update their position. Bar actor equals players actor ID. Because we know they're already in this dictionary, we can go ahead and grab them. And then actor.position.x equals x. Actor.position.y equals y. So now if we run the game, we should no longer see that crazy feedback loop happening. It's just us, and you can tell that we're in sync with the server because we're not getting snapped around like crazy. Our position is being sent to us 20 times a second, and we've coded Godot to update our position according to the server's position, but you can see that movement is still quite smooth. If you want to have proof that this is actually happening in the background, we can go ahead and hack our client and give it a bigger speed than it should have. So we can multiply the speed argument by 2. And maybe it's a little bit more jittery, but you still don't really notice it. But yeah, you can tell something's definitely not right. So let's just undo that. Oh yeah, so anyway, if you connect with 2 clients, you can do that with the debug, customize run instances, enable multiple instances and set this to 2. It should actually be possible to log in as 2 different clients and find each other. The only problem is the world is kind of large. It's 10,000 by 10,000. So the chances of running into each other quickly is pretty slim. We can make it easier for ourselves by allowing the camera to zoom out, and that way we can just zoom out until we can see the other player. So the last thing we'll do in the actor.gd script, we come into objects, actor.gd, is we can override the input event, func input, and we can just say, we only want to do this if the actor is a player, so is player, and event is input event mouse button. So we want to target the scroll wheel, which is technically a mouse button, and event.is pressed. We can match on the event's button index. In the case that it's the mouse button wheel up button, we will zoom out the camera. So camera.zoom.x equals camera.zoom.x plus 0.1. So this is actually zooming in the camera, excuse me. And we don't want to be able to zoom in infinitely. So we're actually going to take the minimum value of just the number 4 with the updated camera's X zoom. So whichever one is smaller. The other case is going to be mouse button wheel down, where we're going to want to zoom out. And we're going to take the whichever is bigger of 0.1 or camera.zoom.x minus 0.1. And we just want to make sure that the Y zoom is the same as the X zoom, so we don't get any stretching. And there we have it. We should be able to zoom in and out using the scroll wheel now. So let's try and find evidence of another player out there now that we can scroll. So I'm going to zoom out. Right. Don't see anyone yet. Oh, there he is. Let me see if I can just swap the windows around to make them move towards each other. And there we go. We can see on both screens Tristan and John frolicking in the world together. And you can see it is quite janky, and this is just due to the fact that every time we see a player that we already know about, we're simply just setting their X and Y position according to what the server sent, and it's not going to be perfect, so we do see a bit of jittering, but in the very next part we're going to work on smoothing that out. So it's far from perfect, but we actually have a game now. We've made some good progress. We added gameplay to our MMO. We can see other players moving around on the screen. So I hope you learned something from this lesson, and if you did, please let me know by leaving a comment on the video or leaving a like. And if you had any trouble or feedback that you want to voice, you can come into the Discord server. And there are currently a few developers who are following this course, sharing ideas and sharing progress. So feel free to join. Otherwise, you can just leave a comment for me in the YouTube comments, and I'll be sure to get back to you. And as always, I hope to see you in the next video.